Thanks for coming to the Tartan SLAM Series talks. I'm Huayu from the AirLab. Today we will have two presentations of visual and LiDAR SLAMs. The first talk is pushing the limits of visual SLAM, given by Dr. Wenshan Wang. She is a project scientist at the Robotics Institute. His research interests are applying machine learning to robotics problem and improving the robotics and the intelligence of autonomous robots. Her research has been focused on off-road driving using learning dynamic models, autonomous air filming, inverse reinforcement learning, semi-supervised learning, robot task planning with uncertainty. In this talk, she will introduce her recent works on large-scale diverse SLAM dataset TitanAir and learning-based VIO Odometry TitanVO. Welcome, Wenshan.
Thank you, Huai, for the introduction. Let me share the screen now. Okay. So today I'm going to talk about the visual SLAM. So because of all these nice features of visual sensors, visual SLAM is a very important research direction. So however, visual SLAM algorithms are still not as robust as widely used LiDAR SLAM in real applications. So in this talk, I'm going to discuss the following two questions. First, we are trying to identify the limitations of the current visual SLAM algorithms, trying to answer how do visual odometries, visual SLAM algorithms perform in challenging scenes. And second is we want to discuss how can we improve the robustness of visual SLAM and visual odometry methods. So first, let's think about how a visual SLAM algorithm is evaluated. So researchers usually test their algorithms on openly accessible data sets. For example, these three data sets are among the most popular ones for the visual SLAM task. I found these figures in visual SLAM paper showing the results of the state-of-the-art visual SLAM algorithms. They look very good. And if you look at the Kitty benchmark, people are competing over high accuracy down to 0.01 or 0.001 precision. So, but when we put these algorithms on a real vehicle or drone, it usually fails in all kinds of ways. So one problem is for these data set, so the data is lack of diversity. So each of the benchmark listed here only covers one or two types of scenes, and they are relatively clean comparing to the messy cases in the real world, and they provide relatively small number of labels from the perspective of deep learning area. Furthermore, the motion patterns are constrained by the data collection setting. As you can see in the bottom figure, so we did a PCA on the camera motions for different data sets. The figure shows the three principal components for the translation and rotation respectively. So the data from Kitty has one dominant axis, both in translation and rotation. Because the vehicle is mostly moving straight forward, combining with small left and right turn, so which is like a 2D motion. So the URAC data set is collected using a UAV, which would have less pitch and roll motion. And for this TUM RGBD data set, it is collected by handheld camera. We can still see the bias, the motion bias here. So the lack of motion diversity here has two limitations. First, this simple motion is insufficient to test the visual SLAM algorithm. And secondly, learning-based algorithms trained on this data, these kind of data would not be able to generalize to other types of motions. Therefore, we need a better testing benchmark with the following features. We need diverse testing scenarios, more challenging scenes, diverse motion patterns, and for learning-based methods, we need large amount of label data. As we can imagine, collecting real-world data is really expensive. It often relies on elaborate sensor setup and careful calibration. And the ground truth for the SLAM algorithm usually comes from other high accuracy sensors such as LiDAR, GPS, and motion capture system. So another thing is the data distribution is often biased, constrained by the physical properties of the hardware. So instead of set up a physical system, so we take advantage of the photorealistic simulation environment AirSim, which is developed by Ashish and his group from Microsoft. The simulation provides reliable ground truth labels with very low cost. However, one biggest issue is known as sim to real gap. So which means the algorithm trained on the simulation the performance will drop when you test it on the real data. So how can we overcome this problem? Our solution is to use large size to increase the size and the diversity. So this idea is borrowed from the successful story of domain randomization. So namely, increasing the diversity of the environment, the model learned in simulation can be easily generalized to real world. So in our TitanAir dataset, so we set up a diverse scene, including urban, rural, domestic, public, sci-fi, and our dataset contains large amount of label data, which is an order of magnitude larger than existing ones. Besides, we lose the motion constraint, which results in an unbiased motion pattern. So this year, we've been working on a second version of the data set. So we plan to add more environments, more trajectories and frames. And we've been working on adding new modalities, including IMU, LiDAR, spherical camera, fisheye camera, event camera, radar. And we also added more variations in the acceleration motion patterns to make it less and less biased. Yeah, we've also added dynamic objects, including vehicle, pedestrian, animal, leaves, and so on. So this is a overview of the challenging features. For example, the changing the lighting changes and the night scenes, adverse weather, dynamic objects. So next we can start to answer the question, like how do visual SLAM algorithms perform in these challenging scenes? We've tested a bunch of algorithms. So here in the table, we show the ORB monocular and ORB stereo algorithms on 8 of our trajectories in the data set. So we use ATE, the absolute trajectory arrow, and RPE to evaluate the trajectory. As you can see here, the arrow is very high. but we found these metrics, AT and RP, are not sufficient to distinguish the performance of the algorithms, because the algorithms often lose tracking of the camera pose. So here we present another metric, valid rate, which means the percentage of the successfully tracked frames to evaluate the trajectory. So this indicates like more towards the robustness instead of the accuracy. So under this metric, we can see the monocular algorithm only have 50% average value rate, and the stereo algorithm is a little more robust, has about 70% value rate. So as a comparison, this is the performance of the ORB stereo algorithm on Kitty dataset. So you can see the huge gap. So which indicates the challenging features of our dataset. So we found many interesting failure cases. The figure shows where the ORB monocular algorithm lose tracking of the trajectory. So typical reasons are getting close to an object, the moving objects, and illumination change, the dynamic objects, in this case, falling leaf, and reflections. In the stereo case, it is more robust to moving objects and illumination changes. So we found many failure cases are caused by lack of features. Also, the reflections and moving close to an object also bring some challenge. So in terms of learning-based method, are they more robust? So most of the learning-based methods are not even be able to test on our data set. So they cannot be generalized to unseen data set. So we can see at least two problems. First, the models, the learning-based models are often trained on specific types of scenes with specific motion bias, for example, the Kitty data set. And another problem is they usually neglect some fundamental natures of the problem, which is well formulated in geometry-based VIO theories. So one problem is the camera intrinsics. For example, a different data set has very different camera intrinsics. So this makes the relation between input and output very different. So if you train on this type of data, KT data, so it is not able to test it on other kind of data set. Another fundamental problem for monocular SLAM is the scale ambiguity. Because monocular algorithm has only one camera, and it just cannot recover the true scale of the motion and the geometry of the scene. So how can we learn a robust and generalizable visual SLAM method? So we proposed a simple model, TitanVO, which explicitly deal with these three problems: the scale ambiguity, the training data, the diverse training data, and camera intrinsics. So we designed this simple odometry model with two-stage network structure, following the idea of geometry-based methods. it consists of a matching network, which outputs dense per pixel matching between the two consecutive frames, and a post network estimating the camera motion, camera translation, and rotation. So first, we tested directly, tested the scale ambiguity issue. So we trained a network to estimate directly the full scale camera motion. So we used 17 environments for training and 3 environments for testing. We observed a significant gap between the training and testing losses. So if we plot the translation loss and rotation loss separately, we can see the gap is mainly caused by the translation loss. So which is exact as what we would expect with the scale ambiguity issue. So a simple fix would be, instead of regressing the full scale translation, we only regress the direction of the translation. So we normalize the translation factor in the loss function. After doing this, the gap between the training and testing is decreased. So so we tested the generalization ability on models trained on different amount of data. So as we expected, increasing the amount of diversity of the amount of the data, we can see it helps to reduce the generalization gap. And the last issue we want to solve here is the intrinsic ambiguity. So take the images from these 3 data sets, for example. The resolution and field of view are very different. So one straightforward idea would be just to warp the input image to a same intrinsic setting. But if we warp the kitty data set here, the kitty image here to align with the TitanAir intrinsics, there will be a lot of paddings. So if we do the other way around, we will lose a lot of information. So our solution is to take the camera intrinsics as another input. We design this intrinsics layer, which is a 2-channel tensor encoding a 2-channel tensor, and it encodes the intrinsics in XY directions separately. So to train the model with different camera intrinsics, we do random resizing, random cropping and resizing over the input data from TitanAir dataset, as you can see in the table here. So with random cropping and resizing and train on a model with intrinsic layer, we can achieve the best testing performance. So we compared the TitanVO model on various data sets. And yeah, this model is only trained on the synthetic data on TitanAir dataset. So we tested on KT, you can see comparing against both learning-based and geometry-based methods, TitanVO achieved results comparable to these baselines. And yeah, without fine-tuning and without doing bundle adjustment over multiple frames. So on difficult sequence from URC and TitanAir datasets, so our TitanVO model outperformed geometry-based methods, which are less robust and fail to track some of the sequences. like these difficult ones. So here we showed some visualization of the visual odometry model. So the red line is output by our model, and the blue line is our baseline, the ORD SLAM baseline. You can see the ORD SLAM usually takes some time to do the initialization, and it will lose tracking on some difficult frames. Here's some more example. We have challenging scenes like here's a very noisy, the dusty environment, and the indoor environment typically has less features when the camera facing the white wall. We also tested on QT data sets, and yeah, it without any fine tuning, just output like reasonable trajectories. Also, some tests on the Europe data set. It's a little bit more challenging than QT because there's a lot of motion blur and some illumination changes as well. Yeah, this shows the trajectories output by our algorithm, by our model. Yeah, we also collected our own data like using handheld camera. So we only use the left camera as our input, and we compare it against the commercialized RealSense T265. Yeah, it also loses tracking when there's very aggressive motion, and yeah, our model can track the whole trajectory. Yeah, to summarize, so we published the TitanAir dataset aiming to set up a benchmark to evaluate the visual SLAM algorithms on challenging scenes. And the state-of-the-art visual SLAM algorithms are not very robust when testing on our dataset. We further developed a TitanVO model, which can be generalized to various data sets without any fine-tuning and outperform the state-of-the-art algorithms in challenging cases. Yeah, okay, that's all for my presentation. And please check out our website for our dataset, and our code is also public available here. Thank you, everyone. Yeah.
Okay, thank you for the great talk, Wenshan. And we will leave the QA session to the end of two talks. Okay, let's go to the next talk. The next talk is from Shibo. Shibo Zhao is a first-year PhD student at the Robotics Institute at Carnegie Mellon University. He is advised by Sebastian Sachir, and he serves as a SLAM engineer at the Team Export competing in the DARPA Subterranean Challenge. He designed the SuperOdometry and the TPTIO odometry for the Team Export, which are adopted as a major method to achieve state estimation. His focus on SLAM in challenging environments. Also, his interest in related topics, including multi-sensor fusion and deep learning. In this talk, Shibo will mainly talk about his recent IMU-centric LiDAR visual inertial estimator, SuperOdometry. Okay, welcome, Shibo.
Hello, everyone. Thank you for the why. Today I would like to introduce SuperOdometry, IMU-centric leader visual inertial estimator for challenging environments. So can you hear me? Why?
Yes, we can hear you.
Oh, okay, thank you. Okay. So hello, everyone. My name is Shibo. I'm the first year PhD student in Carnegie Mellon University. Today, I would like to introduce our recent work, SuperOdometry, IMU-centric leader visual inertial estimator for challenging environments. For this talk, I will mainly talk about how to achieve robust state estimation in subterranean environments. This work is developed in the context of the DARPA Subterranean Challenge, which will help our robots to navigate internal, urban, and cave environments. Robust simultaneous localization and mapping is a fundamental need to achieve high-level autonomy for mobile robots. The question of is SLAM solved is often asked within the robotics community. From my perspective, the SLAM problem is only solved in short-term normal scenario. It still easily fails under challenging conditions such as visually degraded environments or geometry degraded environments. Because of these challenges, our robots still find it difficult to achieve long-term autonomy. To solve this problem, we believe that an ideal SLAM solution should be fail-safe and failure-aware. For example, the system needed to be aware of imminent failure due to outliers, degeneracies, or hardware failures. In the last decades, multimodal sensor fusion has gained great popularity and can be classified as either loosely or tightly coupled method, as shown in the table 1. Loosely coupled methods have been preferred more because of their simplicity, extendability, and low computation expense. In contrast, tightly coupled methods have brought more advantages for their accuracy and robust performance. So why not combine these advantages together? Instead of combining all sensor data into a full-blown vector graph, SuperOdometry divided the big vector graph into several sub-vector graphs. Visual odometry vector graph, laser odometry vector graph, and the IMU-odometry vector graph. For each sub-vector graph, it's a tightly coupled based method, since it directly processes the raw measurement of the sensors. While between the vector graph, it's a loosely coupled based method, since it only transfers the initial guess and pose constraints. Therefore, it combines the tightly coupled method with loosely coupled method. Here is an overview of the proposed system. You can see that it's composed of 3 modules: IMU-odometry, visual inertial odometry, and leader inertial odometry. The estimated states can be written as this equation. You can see that not only the pose velocity, but also the accelerometer bias and the gyroscope bias. Our system design follow a key insight. An IMU and its state estimation can be very accurate, as long as the bias drift is well constrained by other sensors. Therefore, SuperOdometry uses the IMU as the primary sensor. It uses observation provided by visual inertial odometry and leader inertial odometry to constrain the accelerometer bias and the gyroscope bias. In return, the constrained IMU odometry provides the prediction to the VIO and LIO system, which recovers motion in a coarse-to-fine manner. So why IMU-centric SLAM? Why IMU-based SLAM? The major reason is that other sensors-based SLAM systems, such as leader SLAM or visual SLAM, are not environment dependent. Compared with these sensors, IMU is very robust and is not environment dependent, and it doesn't have too many outliers. Here is a comparison between the IMU and the visual camera. You can see that the only drawback of IMU is that it cannot achieve accurate state estimation in long term. Because of this, SuperOdometry regards the IMU as the primary sensor. The structure of an IMU-odometry vector graph is shown in this figure, which is similar to the traditional pose graph structure. However, it's different, since the estimate state of IMU-Odometry not only contains the poses, but also the accelerometer bias and the gyroscope bias. Each node in the pose graph is associated with a state. The edge between the consecutive nodes represents the relative body motion obtained from the IMU pre-integration factor. In really degraded environments, where all relative pose factor will have a lower weight. In contrast, in geometrically degraded environments, LIO relative pose factor will have the lower weight. Note that the IMU-Odometry can also incorporate the measurement from other sensors, such as the GPS and the VIO odometry, as long as the sensor can provide the relative pose to constrain the relative position and the orientation of IMU pre-integration. These sensors will be fused into the system successfully. Okay, let me introduce our visual inertial odometry pipeline. For front end, we track monocular visual features and the laser point within the camera field of view, and use the laser point to provide the depth information for visual features shown as the figure A and the figure B. For the back end, we adopt to use the Wenshan pipeline. For each new frame, we minimize a nonlinear optimization problem that consists of the visual reprojection factor, IMU pre-integration factor, marginalization factor, and a pose pariah for the IMU odometry. The structure of the visual inertial odometry factor is shown in the figure C. Remember that IMU odometry can be constrained by other sensors. Therefore, when the environment is visually degraded, the IMU pose factor will be dominant in the optimization problem. However, when the environment has good lighting conditions, the visual factors will be dominant. Here is the structure of our linear inertial odometry factors. We minimize a nonlinear optimization problem consists of the multi-metric SEP factor, IMU pre-integration factor, and the IMU odometry pose factor. Multi-metric SEP factor will include the point-to-point, point-to-line, and point-to-plane correspondence. Similarly, when the environment is geometrically degraded, since the IMU odometry can receive the measurements from other sensors, the IMU odometry is still reliable, and the IMU odometry pose factor will be dominant in the optimization problem. Meanwhile, the unreliable leader constraint will be rejected and set low weight by evaluating the quality of the constraint. On the other hand, when the environment is well structured, the multi-metric SEP factor will be dominant in the optimization problem. Here, I would like to introduce how SuperOdometry overcome the sensor degradation and adapt to various environments. SuperOdometry adopts a novel selective fusion strategies, which automatically select the most informative constraint. In normal thermal environments, since there is no temperature difference in the environment, the thermal camera will be degraded. So we mainly use the constraint provided by laser and visual sensor to achieve the laser visual inertial estimator. In really degraded environments, you can see that there are a lot of dust. We will use the thermal camera instead of the visual camera and achieve the laser thermal inertial estimator. In geometric degraded environments, you can see that it's a long corridor. You will use the thermal and the visual camera to achieve the visual thermal inertial estimator. Since the SuperOdometry uses the multiple state estimation engine, it will distribute the sensor failure risk between the several estimation engines. Therefore, it has a more robust performance to overcome the hardware failures and sensor degradation. So one question arises. So how to achieve the selective fusion? I mean, how to decide if we need to switch the sensor or not? For laser odometry, we combine the feature information matrix with 3D feature distribution together. We use the inverse condition number to detect the degeneracy and use the 3D distribution method to find a specific degenerate direction. In figure A and figure B, blue circle in the center shows the robot's position, and a small red circle shows the 3D features. Compared with these two figures, it's clear that the feature distribution in figure A may cause large position error since all the features are linked to one direction. For more detail, we refer you to read the following papers at IMU SLAM. Finally, we categorize the 3D leader feature points based on its observability. We test our method on kitty dataset. In this figure, you can see that the red points are the features good for X direction. Green points are features for Y direction. And the silver points are good features for Z direction. Blue points are features for Y direction. You can see that the result looks reasonable. For VIO odometry, we propose to use the feature tracking knob as well as the tooth freedom chi-square distribution to monitor the feature reprojection error in a sliding window of the VIO system. Since the special motion, such as the constant velocity, pure rotation, may also cause the VIO system unreliable, we also monitor the motion of the robot to detect the degeneracy. The next problem is the time synchronization problem. We all know that the time synchronization will be very tricky for the multiple sensor fusion. The left figure shows the factor graph of the traditional laser visual and IMU fusion. Since all the measurements should be ready at the right time, it requires very good time synchronization. Also, it fills all the constraints in a single optimization. It will be very difficult for them to achieve real-time performance. In comparison, since all the subsystems in SuperOdometry can output 200 Hz and use relative pose constraints to connect to other sensors, the system will not be very sensitive to time synchronization, and the relative pose actually can be generated at any time by using the linear interpolation method. The constraint is dependent by the request time, not the internal clock. Therefore, SuperOdometry supports sensor fusion asynchronously. Here, I would like to introduce the experimental result of SuperOdometry in geometrically degraded environments. In this experiment, we ran SuperOdometry in the long corridor environment. We compare SuperOdometry with another famous work, LIO SLAM. You can see that the LIO SLAM begins degraded in such environments because of the lack of constraints in the forward direction. We can observe that there is a big misalignment and significant drift, as shown in the yellow circle in the LIO SLAM. SuperOdometry, on the other hand, can still work well, and the mapping result of SuperOdometry looks good. We also test SuperOdometry in really degraded environments. In this data sequence, We hand-carried the sensors and worked past a poorly lit room combined with aggressive motion. The image is mostly dark. However, SuperOdometry automatically rejects unreliable visual constraints and make use of the laser constraints to achieve robust state estimation. Finally, we test SuperOdometry in both visually and geometrically degraded environments. In this experiment, the SuperOdometry was running with autonomous flight in cave environment. It shows the algorithm's ability to overcome the airborne obscurants. You can see that both LIO and LIO SLAM fail to create an accurate map in the scene. Since SuperOdometry can select the most informative measurements and reject the outliers, they can still achieve the robust state estimation in dust environments. The built map is very accurate. The estimated trajectory is around 500 meters, and the endpoint error is around 5 centimeters. In darker subterranean challenge, we also needed to overcome the smoke and dust environment. To solve this problem, our solution is to fuse the thermal inertial odometry to SuperOdometry pipeline. Here is a video showing the performance of thermal inertial odometry outperforms leader odometry when environment has a heavy smoke. When entering the smoke environment, leader measurements degraded, while thermal images are still clear and provide useful information. You can see that even though the features are not sufficient, our thermal inertial odometry can still robustly estimate the ego motion. In the end, we observe that our method has a smaller drift comparing with the leader odometry. Our thermal inertial odometry is based on our another work, TPTIO, a robust thermal inertial odometry with deep thermal point. Because of limited time, I will not introduce the principle this time. For more detail, we refer you to read this paper. Here is a quantitative comparison between the state-of-art method with SuperOdometry in previous challenging environments. You can see that SuperOdometry is more accurate and robust. SuperOdometry also supports multiple platforms. Currently, it supports OS 1, OS 0, and Wenshan. It has also been tested the UGV, UAV, and it will also be tested on the legged robot. Finally, let me summarize the main advantages of SuperOdometry. First, we propose an IMU-centric sensor fusion architecture, which enables us to achieve robustness and extendability, since it combines the advantages of tightly coupled method with loosely coupled method. Second, we think that the SuperOdometry is simple and effective, since it avoids the complex math to fuse the multiple sensors. The reason is that the IMU has a very simple and accurate probabilistic model, as long as other sensors can provide the relative pose prior to constrain the IMU pre-integration factor. These sensors will be fused into the system successfully. The third one is that the SuperOdometry divided the big factor graph into several subfactor graphs, and each subfactor graph receives the prediction from the IMU odometry. Therefore, the motion from each odometry factor is recovered from the coarse-to-fine manner in parallel, which significantly improves real-time performance. So the main idea I want to share with you today is that we learned that IMU is a very powerful sensor for the state estimation, and it can be extremely accurate as long as the belts can be constrained by other sensors. Okay, thanks for your watching. for more experiment, you can just use this QR code. Thank you.
Okay, very great talk. Thanks, Shibo. And we first leave questions. If you have any questions, want to directly ask them, you can unmute yourself, and yeah, we can communicate with each other. Okay, maybe we can first go some questions on the meeting post. Okay, the first question is to Wenshan. How to fuse the inertial sensor data to TitanVO model to make it like a very inertial odometry?
Yeah, this is a ongoing research direction we are currently working on. So yeah, we've tested different structures. I think it's yeah, totally possible. So some of the most straightforward thing we have tested is just train an integration model over the IMU data and combine the IMU odometry and the visual odometry together in a later stage. Yeah, that's and I think we are still working on that, and yeah, we encourage more people can join us and train some models, not only the VIO, so we can also do incorporate LiDAR and other sensors like the event camera, the spherical camera we are going to add for the second version. So yeah, I imagine we will have more robust models after we adding more sensory modalities, and there's a wide range of research directions we can do utilizing these data.
The second question is to Shibo. In SuperOdometry, how do you switch the sensor data between LiDAR and visual observations for different degenerated environments? Like some environment are visual degenerated and some are geometry degenerated. But in your experiment, you just to configure your SuperOdometry to the environment. I mean, sometimes we don't know what environment it is. So how do you switch the sensor observations?
Yeah. Well, I think this is a good question. I mean, for the switch scheme, actually, it definitely depends on the degeneracy detection from your visual odometry or laser odometry. So basically, in our DARPA subtraining challenges, because we all know that laser odometry is more robust than the visual odometry. So basically, we will try to regard the laser odometry as the main sensor. So we will use the laser degeneracy to check if the status of the laser odometry is good or not. So if the laser odometry is not very good because of the degeneracy, we will request the visual odometry to provide the actual constraints for the laser odometry, and then to help the laser odometry to overcome the degeneracy environment. So basically like this.
Okay, so when there's some geometric degeneracy, you added the visual constraint, right? But by adding visual constraint, the computation burden will be greatly increased, right? I mean, processing visual data is always a more CPU computation have more computation complexity. So when you add in visual or thermal constraint, it will sometimes make there some latency for the post estimation, right?
Yeah. So yeah, I think for the SuperOdometry part, since we only fuse the relative pose from the different sensor modalities. So for example, when we fuse the thermal, visual, and laser together, we just try to fuse the relative pose, provide different source of odometry. So because it's a pose, so you don't need to find it's different to try to fuse the correspondence. So the CPU usage actually will be very low because the pose measurement actually didn't takes a lot of CPU usage and didn't and when you add into your optimization problem. So based on this, I think the CPU usage will be not very large.
Okay, yeah. So if by using this kind of loss coupling, so you use like the IMU measurements for multiple times, right?
Yeah.
Okay.
So here I want to clarify. So when we try to fuse the IMU measurements, we need to make sure that if the measurements is a raw data or if this IMU measurements are already constrained by other source odometry. So in the SuperOdometry pipeline, for visual inertial odometry, laser inertial odometry, or thermal inertial odometry, this initial part is just try to fuse, it's a raw measurement. We just use a raw measurement to fuse in the different sensor to their odometry part. However, for the IMU odometry, because it fuse all the IMU odometry, it use all the other odometry to constrain the IMU part. So it maybe this part maybe it has some dependence issue, but for other odometry source part, since we only use the raw data, so I think it's it will not make the odometry independent.
Okay, yeah, it makes sense. And then we have another like a question for both of you. This is my question. Is there any unified measurement to measure or to estimate the challenge level of the environment? Like instead of some definitions of illusion changes or geometric degeneracy. Like this, usually like even for the learning based or geometric based, you only like look at the environment first to determine if it's visual degenerate or geometry degenerate. So is there any kind of environment or unified algorithm that can measure the degeneracy of visual or geometry?
Yeah, that's a very interesting question. So from the perspective of visual SLAM, yeah, I think to say like which kind of environment is more challenging is a difficult one, because yeah, the challenging like how challenging it is really depend on like what kind of algorithm you are using. For example, if you are using like feature-based method, like the featureless environment will be very challenging for you. And like, for example, we tested DSO, which is a semi-dense algorithm. It is less likely to, less vulnerable to featureless environment. Like the dark environment is perform better. But if you have more aggressive motion, yeah, it usually causes a lot more problem than feature-based method. So yeah, in my understanding, how challenging it is, it's algorithm dependent. Yeah, it's not very easy to define like a metric to evaluate like how challenging the sequence is. Yeah, so our dataset is really trying to provide all kinds of challenging cases according to what we will encounter in the real life. So hopefully we can cover more and more challenging cases and be better benchmark.
Okay, so by that way, we can use data-driven to make the algorithm that can overcome all the challenges, right? Just by
yeah, that's our
learning.
hope. If you can test on our data set, you can identify the disadvantage of current algorithm and trying to improve that.
Yeah. Shibo, do you have any opinions?
Right now I don't have. Yeah.
Okay. Yeah, so for the geometric degenerated environment, so currently you are based on the I'm also thinking about some ways to for your SuperOdometry, you want to fuse both LiDAR, visual, and thermal together. So is there any way that to just associate all the visual LiDAR and thermal features in the front end to sometimes the geometric doesn't work, but the visual works. So it's like the tiny coupled method. So do you think this will be the future of this kind of like multi-sensor fusion for serialization?
Okay. Yeah, I think from practice, definitely if we can fuse the measurements such as visual landmark, thermal landmark, and laser features together into a single optimization problem, I mean, you could probably can get the best optimal result. But the drawback of this is that since if you need to prepare all the correspondence before the optimization part. So that means that this correspondence will take a lot of CPU usage. And also that means, and also because you need to fuse this at the right time. So that means it also has very high requirements for the time synchronization. So compared to this pipeline, so SuperOdometry is just to try to fuse the VIO pose or thermal inertial odometry pose in the optimization problem. So maybe this solution may be not very optimal, but at least it can provide the suboptimal choice for the estimation. So it can make sure that the whole solution will be degeneracy or diverge. So I think that's different. But I think it's also so how to choose if you choose a SuperOdometry or other technical method. I think it's just I think this question depends on your CPU usage or your CPU resource on your computer. So I don't think it has a certain answer. I think it just depends on the environment or depends on your device.
Okay, we have another question for Shibo. Can we also get this kind of stable results for like a sub-T environment with different LiDAR sensors, like a Levox or Oyster?
I didn't. So for the Levox, actually, I didn't try SuperOdometry on the Levox, but I think the major modification will be the feature extraction part. So I think it may be not very difficult to achieve. And for the Oyster laser, we have already tested the SuperOdometry on the Oyster, so it works well.
Okay.
Yeah, I have another question for Shibo. So when we tune different sensor to fuse different sensor, if there are any weights you need to tune, like is it very hard to tune the weights? Do you have to like tune the parameters for different types of environment? Like if you have a cave environment or a subway environment, would the weights be very different?
Yeah. For the optimization part, I think the most tricky is that how to balance the weight between the different factors. I think one way we need to make sure that if you really need to, for example, in the SuperOdometry part, we try to fuse the relative pose factor in other VIO system or LIO system. So to make sure that when you fuse the VIO and LIO relative pose factor in the system, you need to tune the weight is basically equal to the rest of the weight of the factor. So make sure your weight actually will be influenced in has the same weight with the other factors. So I think this is one rule I follow in practice. But basically, if we need, I think it's just the engineering skill. I mean, it's if we need to find a more better solution to how to tune the weight, I think it still needs some time to discover.
Okay, thanks.
Yeah, we have maybe the last question for Wenshan. How do you handle the dynamic objects in TitanVO?
Currently, yeah, we didn't explicitly handle the dynamic objects. So we do have some dynamic objects in some of the training data. So that's implicitly handled. So we've been working on recently another model that incorporates uncertainty estimation into the model. So that can handle dynamic objects better. The way we do it is we estimate the uncertainty for the optical flow estimation and the motion estimation. So whenever we see the dynamic objects, so usually, yeah, it can if the dynamic object takes like a large field of view of the image, then we can see the increase of the uncertainty level.
Okay, yeah, I think this is also the current very popular topics for the odometry, for the SLAM, right? For the dynamic objects for autonomous driving or for mostly for autonomous driving. You need to mask or use that kind of dynamic objects to make your serialization more robust.
Right. Yeah. Yeah. To estimate the dynamic objects like explicitly would be a very interesting way to go. I know some unsupervised method already using that like estimate another output, like encoding the moving part of the scene. Yeah.
Okay. Yeah. Thanks for the great talks.
Yeah. Thank you.
Okay. Thank you.
And yeah. Thanks.